So, good morning, everybody. We'll start with the topic today on direct digital converter for resistance sensors. If we recall that we have already discussed several resistance sensors, RTD, strain gauge, thermistor, and etc. And we have seen most of them employ bridges and obviously afterwards some signal conditioning circuits and etc. We will be discussing about few more afterwards, but if we look at the overall just consider that any resistive type the sensing systems or instrumentation systems are like this. You can say conventional schemes for resistive sensors, conventional measurement scheme. So you can easily see that basically this is a sensor. We have a resistive sensor, so the resistance of it changes there. And from there we have a signal conditioning circuit. We have a signal conditioning circuit which may constitute of bridge, amplifier, filters, and etc. Then we have that one, but often gives you an analog output. But often we require a digital display, and this signal has to be converted into some digital signal here. So for that one, what we require, you can say a sample and hold circuit. Then it would go to some ADC. Then you can say that it goes to a MCU, that is a microcontroller unit. And here we get a digital signal, and this microcontroller unit is for display and other purposes. Maybe you need to transmit the signal over a distance, or you need to send it to a controller or like this. So if we look at it, we have already told this is the basic sensing system. This is the signal conditioning system, which has got several in between blocks like bridge, plus amplifier, plus filter, etc. And here the sample and hold ADC, then digital output signal. So naturally a lot of hardwares and are involved in this one. So idea for direct digital converter that is the DDC is that whether we can do away some of the components there and directly measure the resistance variation of the sensor, just directly give it to DDC, direct digital. That means the resistance variation will be directly converted into some digital signal there. Binary signals are like this, and there after it goes to the microcontroller unit. So basically you can easily see that we can do away much of these things there, we can make it more direct digital measurement, and naturally this will be easier for handling, and some of the noise sources and etc. can also be eliminated in this way. So that's the basic idea of this one. We require a direct digital converter. You can easily understand that in this DDC we have we have an inbuilt AD converter. We'll see it. It has got an inbuilt AD converter, and maybe this sensor may be also inside the DDC. This sensor may be inside the DDC, so that a compact DDC will give you a direct digital output which is proportional or a function of the input variable, that is the variation of the resistance. So naturally you can see that this technique is now becoming popular, since we have got uh, and this we can do away a lot of bridge, amplifier, filters and all these things. So component cost will be less, and measurement could also be simpler. So naturally these things are coming nowadays. These are new features where you can have a ADR, and we will see afterwards also that this direct digital converter is applicable, actually can be used not only for resistive sensors but this capacitive sensors as well. So we can use the resistive sensors, this direct digital converter using resistive sensors or capacitive sensors as well. So first of all, any type of resistive sensors, we can use this one and get a direct digital signal. But first of all, the question is that how does it work? So for that one, if we recall, in your measurement class must be before going to the DDC, so in our measurement class you must have studied a dual slope AD converter in dual slope ADC. We have seen that one, the one of the basic technique for converting any input voltage to a digital signal. That is the thing which we have already seen. There's dual slope in most of the digital multimeters and etc. They employ this dual voltage measurement, a dual slope integrated type ADC, which is rather a bit slow, but it has got several advantages also, and it is simple. So first of all, let us try to recapitulate what we had studied in our dual slope ADC. Then we will go for, actually we will see that DDC can be evolved from this ADC itself. See, what we had is that, if we recall, So this is the basic principle of a schematic arrangement of a dual slope integrated type ADC, which is very primarily constitutes of a R fixed and C there is an integrator here, and followed by a comparator, which basically which is acts like a zero crossing detector. So at every crossing of the zero of this V0T, it will change its output, digital output there. And what we do is that, and this control and logic unit, which is inside the microcontroller, which actually coordinates this one, and such that, and it it moves from floor 1 and 3, toggles from 1 and 2 accordingly to the command of logic and control and logic unit. And there is a counter which gives these pulses are sent to the counter and which counts and finally gives you a digital measurement to the display unit. So I am not showing the display unit, which is like. So I hope all of you know these things there. And so what we know that this is for preceded by what we every measurement is preceded by an auto zero phase. Is preceded by some auto zero phase where uh, the output is made zero, because in case of any offset or this one charge present in the capacitor, feedback capacitor, it is made to zero by force there. So that I just exclude from our discussion. So we say that assume at t is equal to 0, V0t is equal to 0 initially. That means it is auto zero phase. After the auto zero phase, this is in that position, the V0t is equal to 0. And the switch is at position 1. So what we can say that V0t is equal to minus T by RC into V in. It's a positive voltage. V in, I just give it like this. And it has got zero initial condition. It is like this there. And this one, the switch is at position 1 for fixed period T1. The switch is at position 1 for a fixed period T1. So in that case, what will happen is that at t is equal to capital T1, V0, we call it a Vp, is equal to minus of T1 by RC into V in. And we know that if we look at it with the timing diagram, t, and this is t is equal to 0, initially for a fixed time of t1, this voltage V0 will decrease linearly with time there. And then after that one, so The switch is, I call it switch S, say, is connected to position 2 at t is equal to capital T1. So at this position, the switch is connected to position 2, that means the voltage is minus VR. So if it is minus VR, which is a fixed reference voltage, what will happen? So the voltage will be rising because it was still this 1 plus V in, the voltage was negative, and here it is minus VR. So the voltage will start increasing and go for a particular time of t2 there till it becomes 0 there. And then comparator gives you some output, change in output, detects the change in output and do that thing there. So we can say is that V0t for t greater than t1, we can say it is initial condition, it is minus of T1 by RC into V in plus of what we can say it is T minus T1 divided by RC into V dot. So it is the initial value, this is the initial condition there, and plus of T minus T1 by RC into V R. And this is the time T2 at t is equal to t1 plus t2, the V0t is equal to 0. That means it goes onto the 0 level at this point where the signal again goes there. So if V0t is equal to 0 at t1 is equal to t2, we can say that this is equal to 0 is equal to minus t1 by RC into V in plus of T2 divided by RC into VR. So from that one we can say that V in voltage is equal to T2 divided by T1 into VR. That one already we know, we have studied this one, and basically the T2 and T1 are actually there is some clock there and measured using the a counter and for that clock there. And once it comes to the 0 value or there, again the switch is going back to V in, and this way it will continue like this. So this is V in and this is minus VR is a reference voltage. That means a constant voltage there. Okay. So if we know what is the reference voltage, if we can measure the T2, the T1 is already fixed by some design, and we can measure the V in voltage by this one. This is the principle of successive it is a dual slope integrated type ADC, which we have. You can find out any book, even that Cedra Smith, Millman, Grabel also, this will give you the basics of ADC. And this successive the dual slope integrated type ADC is a little bit slow, but the point has got, it is particularly useful if there is some 50 hertz interference like this there, because this is an integrated type. So it integrates the interference of 50 hertz and brings it to total effect to 0 there. Anyway, so we are convinced that this input voltage I can measure this one there. What if, say suppose I can consider it, say suppose this input voltage also I make it constant. And instead of using a fixed resistance R, what we can do is say suppose the resistive sensor is a part of this dual slope integrator. That means this is the resistive sensor I just wanted to change with the parameter there. What will happen? And so theoretically, it is possible if I fix the V in is also constant. So by varying the resistance here, we should be able to come to a similar circuit, I mean with the same scheme, some similar relationship where the resistance, the output, the clocks or the timings would be proportional or would be a function of the what we call it, the resistance values. Then we call them as direct digital converter. But the auto zero phase is there, which I have not included because after every measurement cycle, we should ensure that the capacitance is, there is no charge in the capacitance stored and it is discharged wholly like this there. So what we can say, it is a direct digital converter. We can think of that, okay, that is the A there. I will be making some sort of arrangement where the V in, VR, both of them are known voltage, but the resistance is actually our A there, the resistive sensor there. So in that case, what we can say, we can redraw the things there. Okay, I'll draw it in a different color. So here you can see that I have fixed put two resistors, Rx and R0, and this is Rx is the sensor. And I assume that Rx is equal to R0 into 1 plus Kx. It is 1 plus x kx, where k is a greater than 0. So what we can say, Rx is always greater than or equal to R0, and say suppose it is similar type of RTD or like this sort of expression we can have it. So what we can do is that definitely it passes through an, so what we can say that Rx is always greater than or equal to R0.
Hello, sir.
Yes,
So the input is like minus VR or it is VR?
in the top one is plus VR, the bottom one is minus VR. The switch S can be connected to plus, minus VR, or it could be connected to ground. Can you not see it?
Sir, like we can't see the negative sign. We can like barely see VR.
What up to this one? Which one?
Yes, sir. We can see VR, but we can't see the negative sign.
Oh, oh, oh.
No, sir,
Come.
it's like we are also not visible clearly.
This is
It is clear in the spotlight.
plus VR and this is minus VR. Is it okay? Huh? Is it all right? And this is a switch which toggles between 1 and 2, and definitely in the same way as we had done it. So we have an auto zero phase where we ensure that the capacitor, which circuit I am not showing, which ensures that the beginning of the measurement, the capacitor is discharged fully. And at t is equal to t1, at t is equal to 0, so V0t is equal to 0 there. And, and the thing is that S is position 1. So S is at position 1, that means it is connected to minus VR. So what we can say that for 0 to fixed time t1, what is the value of V0t? We had earlier, whenever it is connected to VR, it is minus of t by RC, sorry, it should be Rx into C into VR. And what would be this one? This will be, because it is connected to minus VR, so it would be plus of t by R0 into C into VR. Got it? So these are all linear elements, we can apply superposition and all the things there. So what we can say is that since Rx is more than R0, so naturally what will happen? This 1 by Rx is always less than 1 by R0. So the voltage will rise in this case towards the positive direction. Mind it, I am assuming K is greater than 0. If K is less than 0, we can make some sort of different arrangement which is not difficult to understand. So what we have it, up to this one T1, we have it and we call it, say suppose this is your V peak. So what is your V peak at T is equal to capital T1, V peak is equal to, what is it? T1 into VR divided by C into 1 by R0 minus 1 by Rx. Am I clear? Is it correct? Okay. So at T is equal to T1, Again, at the same time, at t is equal to t1, the S switches to position 2. If it is switched to position 2, then this is grounded. So, this R0 end is grounded. We can simply think of that it is not there. But the voltage here is now VR. So, naturally, there would be some initial voltage V peak, and due to this plus VR, it will go on decreasing. So, what we can say is that for similarly, t is greater than t1, I can write that V0t is equal to V peak. Then it is minus, because it is now decreasing, it is minus of what we have, t minus t1 divided by Rx into C into VR. Do you agree? So, similar way we had done it in the last time, we are saying like this. So, what we will have is that at t is equal to capital T1 plus of T2. That means this is the thing, it will going to decrease. So, as a result, it will decrease, and this is the time, here it is T1 plus of T2. So, it will be of different slope, but it is of minus plus T1 plus T2 here. So, again that part, then again V0t is equal to 0, and you know that there is a comparator once it is our zero crossing detector. So, at the same time, so the comparator will give you a switch from plus 1 to minus 1 or like this there, which arrangements I am not showing there. So, what I can say is that 0 is equal to minus T1 into VR divided by C into 1 by R0 minus 1 by Rx. And then it is, sorry, not minus, it is plus, because this is the thing I am writing it, minus of what is that? T is equal to T2. So, it is T2 divided by Rx into C into VR. So, or in other words, I can simply write it down that I can simply write it down as, okay, VR and these things are cancelling out. So, it is 1 by R0 minus 1 by Rx is equal to, it is T2 by T1 into 1 by Rx. Please correct me if I am wrong there. Okay. Or, is it all right? Or we can say it is Rx, okay, minus R0 divided by R0, okay, is equal to, because Rx cancels out, so it is T2 divided by T1. Or we know that Rx is equal to R0 into 1 plus Kx, where K is greater than 1. Sorry, K is greater than 0. So, what we can do we can say it is equal to Kx is equal to T2 by T1. So, you can easily see that here this T2, the similar way we had done it for dual slope integrated type, we can just modify it and we get the similar expressions for T2 by T1, and like this, by fixing the T1 value and measuring the T2 value using some counter and etc. I can nicely convert it into a resistance to digital signal, digital output signal conversion, and maintaining the linearity as well. So naturally we can have that, we can do away with many more things there, like parts of the signal conditioning circuits, and by making this sensor as an integral part of the DDC. So naturally, it looks to be very interesting, and like this there, I would. So this one has been taken from the paper a novel dual slope resistance to digital converter, IEEE transactions on instrumentation and measurement by N. Mohan et al. There are three for there, and it is appears in May 2010 there. This paper you can refer it and you can get it always there. So this technique was first proposed by this one, and afterwards has been applied for different type of resistive sensors, and they can have a good, of course we will have to have a, and another thing is that they are not dependent on the absolute value of VR or minus VR, absolute value of C. So if there are also variations, this there would not affect that measurement one. That is the important thing here. And this afterwards also, whatever people have done several modifications and etc. That is another interesting scheme is that DDC for capacitance sensors. Though capacitance sensors we have not studied, but you can easily understand that any capacitive sensor can also be expressed in terms of C0 into 1 plus Kx or like this there. And this way, how to convert, this capacitance variation signal into the direct digital form like DDC. So naturally, this is also, you can try and look it. How can it be? There are obviously several techniques and there, but one of the simplest technique, you can go and do the things there. So, before I conclude, I hope there is no further question. If you have any question, you can ask me always. Before I conclude the resistive sensors, so mostly we have discussed about the temperature sensor, strain gauge, and like this, or even potentiometers. But there could be some other types of resistive sensors. Which we will not be discussing, but I would suggest you please go through the books and have a feel of the basic idea like this, how does it work. But basically, they are mostly this one. One is called hot wear anemometer. That is for flow measurement. If we get time, we'll discuss while flow measurements the principle of hot wear anemometer. Next is what we have it light detecting resistors, or in short we call it LDR. So basic scheme is that if we have this is the LDR, and if it is exposed initially in dark, if it is kept in dark condition, resistance in dark, it would be in megohms. On the other hand, if it is light passes, it is exposed to light, the resistance will be in presence of light, it is in order of kilo ohm. So there is a sharp drop of this one with the light intensity versus resistance. In fact, if we take it, this is a light intensity and this is log of both of them is taking the natural log there, ln of r and ln of I, you will get a straight line. But actually it is, you can easily understand, it is exponentially decaying resistance. So LDR is very important. It's basically some sort of here. Zinc sulfide is one of them, or you can say the materials are cadmium sulfide, cadmium selenide, zinc sulfide, etc. These are the materials we use for this area. Now, we can have also other types of resistive sensors, which are, one is called resistance hygrometer. What is the resistance hygrometer for? Measurement of humidity. Possibly you know this one, resistance hygrometer are basically for measurement of humidity there. In fact, one in earlier days, one of the very effective way for measurement of humidity relative in the atmosphere was like this, is basically human hair. If his human hair is strained and it's exposed to the atmosphere where the humidity is varying, the length of the human hair changes. That's a very interesting thing. So that was the early form of this humidity measurement. Yeah. But here we can draw that hygrometer in a resistive hygrometer. It is basically so this is a hygroscopic material, and here so basically this is a hygroscopic material, some paper or like this who absorbs uh, the moisture, and over which we place some sort of in a similar way we make it strain gauges, some metal foil or like this uh, what we can say is yeah there uh, by coating of metallic coating of this one. So basically two terminals there, and the resistance between these two terminals will be dependent upon the humidity or the hygroscope, which is absorbed by this hygroscopic material. And here also the resistance and the humidity, relative humidity in percentage, and the resistance in uh, log scale, you will find that it is having some resistance characteristics there. So this is also a useful way for measuring the relative humidity of this one. And lastly, I would just show these are all similar, signal conditioning circuits are all similar. So I am not going into detail of these things here. But lastly, I can tell you one more thing is that gas sensors. Often we have to sense some gas, maybe hydrogen, maybe zinc sulfide, hydrogen sulfide, maybe ammonia, or maybe many other gases like this there. So, so many things, gas sensors are there, and they are, and maybe, and also important thing is that with a very minute quantity there. So for even for this explosions, we require to, if there is any explosive stored, to sense that one, we often employ these gas sensors there. These are often used is that metal oxides at temperature above, okay, not above, I will say it in the range (300 to 500 degree Celsius). So the idea is that you heat the metal oxide and let it be exposed with the gas, unknown gas, like this, and the resistance of the element will change, and there is a distinct relationship between the concentration of that gas and the resistance element. So a lot of, so we can say the concentration in percentage, and here it is R, say Rx by R0, that is what you can easily say. Here it is 1, 10, 100 or like that. So you will get some sort of relationship in the log scale there. So this is another application. You will find a lot of applications of metal oxide sensors, gas sensors, for the measurement, for detecting the gases, different gases, so in chemical sensors. But only thing, the problems are different. Metal oxides are being used for different detection of different gases. But only thing is that they are a bit slow, but this is very useful like this. And another type which I will not discuss at all is called Gmr sensor. What is Gmr? Is a giant magneto resistance sensor. So Gmr sensor, actually this Gmr effect is used for detecting magnetic field. This Gmr sensor is for detecting the very small magnetic field, as we have know that Hall effect sensor is used, that one. But Gmr sensor has got certain advantages. There the resistance, it's a giant magnetoresistance effect, is a very I mean, it was rather a recent one. It was developed in 1980s, and the scientists who developed it actually got Nobel Prize in physics there. Uh, so it has got a great impact, but the instrumentation side of it is that the resistance changes, and in fact here also the resistance decreases with the magnetic field, and this can be used uh, for measurement of magnetic field as well, nicely. And some commercial IC chips are also available, which are contain the Gmr sensor and like this. But I am not going into detail. So I will take a break for 5 minutes. Then we have concluded the resistive sensor, and we'll start with the next topic there.